Hello, good morning all. Please let me know whether I am audible. Okay, and my screen is visible. Okay, okay. So welcome back again. In this eighth semester, I will be teaching a digital image processing subject, and along with the theory, we have lab session also for this subject. So somewhat similar to digital signal processing, but the subject is actually different. Different in the sense, there in a digital signal processing, we were talking about time and frequency. But here we will talk about the image pixels and their intensities in a spatial domain and frequency domain. So once we'll start with it, you will get to know what is the major difference. Hope I am saying so. Before I discuss about syllabus of digital image processing, we will first see what actually is an image, and then we will discuss what is there inside a syllabus of this theory subject. Because if you don't know what is an image, if I simply talk about points which are there in a syllabus, you won't be able to understand anything, and you won't be able to grasp the meaning of terms which are there. So first we will see what is an image. So those who have attended a workshop that we had in the last semester, that is applications of Python programming for digital signal processing. So in that we had basically two sessions. One was the introduction to Python and Python programming, and the other was application of Python for audio and image processing. So those who have attended might have some knowledge of what image is and how it is formed. Those who were absent for that session, I will just quickly show you what the image is. Again, in the syllabus point of view, we will be again discussing this point. But before we understand the syllabus completely, you must know what image is. So this is an overview. Okay, I hope this slide is visible. Wait a minute. Okay. So what basically? Wait a minute. Okay. Uh, what basically you see here is a representation of image. Uh, if you see in this leftmost uh, picture, uh, the first thing that is written here is a 0, then 2, then 15, then 0, and so on. So these individual values are called as pixels. Pixel is a basic or the smallest element which forms or which makes an image. Okay, so if you say what is a smallest element in a paragraph, so in the paragraph you have sentences. In the sentences you have uh, phrases. In the phrases you have words. In the words you have single letter. So that single letter is a smallest element available in the textual paragraph. So in an image, if I ask you what is the smallest element, so your answer should be pixel is the smallest element. So what each individual number represents here is called as a pixel. So what you see here, this 0 is a pixel, this 2 is a pixel, 15 is a pixel, and that number represents the value of that pixel. In a black and white image, for example, in a black and white image, if the pixel value is 0, that represents black color, and if the pixel value is 255, sorry, in if the pixel value is 1, that represents the white color. As opposed to this, if I have a grayscale image, grayscale means there is no only black and white, but in between black and white, there are many other shades of gray, and that is called as a grayscale image. Okay, I hope the idea is very clear. Black and white means only black color and only pure white color. No any other color, only two colors. And if I have more levels of intensity or more gray levels in between black and white, that image is called as a grayscale image. So in that grayscale image, 0 represents pure black and 255 represents pure white. In this case, this is a black and this is a white, and in this case this is a black and this is a white. Okay, and in between 0 and 255 there will be varying intensities from black to white. So if number is suppose 230, 230 is very close to white, that means this might be some bright color which is not pure white but bright color. If I say pixel intensity is 10, that means this is a pixel having some darker shade which is close to the black but not pure black, because this is 10. If I give pixel value 0, that represents a pixel with a pure black color. Okay, so in this way we can identify. So the image that is shown here on the left side is a grayscale image. Meaning of this is it has intensities of a pixel varying from 0 to 255. So you can notice that wherever you have a 0, the pixel value 0, the color represented by that is a black. So actually image will be having only colors. They will not carry these numbers along with them, but this is just a pictorial representation to make you understand what an image is. So when you see a pixel, for example, when you see a pixel with value 255, that means the color is pure white. So when you see a pure white color, basically the processor or the programming unit treating that pixel as an intensity of 255. But we as a user, we can just look at that white color. We don't know any number, or we cannot directly relate any number with that color. But on the back end, what programming is doing, programming is reading a number. Suppose it reads 0, it will show a black color on a screen. It reads 255, it will show a white color on the screen. So it changes the illumination. So somewhere, suppose this is my screen. On this screen, if I illuminate this leftmost area very less amount, and if I illuminate this rightmost area with a very high amount, what it will look like? It will look like a left portion as a darker shade and right portion as a brighter shade. So it will be as if it is an image with left side is dark and right side is white. So it depends on illumination. So these numbers basically tell your display unit to adjust the intensity on screen. 0 means no intensity, totally dark black screen, and 255 means very high intensity. So screen will be brightest at that particular pixel where you have value 255. So this is how your image looks like, and how that image is stored and how that image is carried on the programming end or on the computer. The image is carried through the computer as if it is a matrix. So do you see these numbers? These numbers actually represent the image. So along with these numbers, I have shown a image. It is a image of a number 8, right? So while storing on the computer, it will be stored like this. It don't know where is what kind of intensity, but it only knows that the first pixel value is 0, the second pixel value is 2, third pixel value is 255. As I said, pixel is the smallest graphical area which is shown by some specific intensity in a image. The smallest element of the image is a pixel. So this only knows the number. Numbers will be stored in the matrix form, and that is called as an image which is stored on a computer. So on a computer, how image is stored? only a matrix with some number of values. And on a screen, how that image will be represented, just read that matrix. Wherever that matrix value is 0, put black color on a screen. Wherever matrix value is 255, put your white color on a screen. And wherever values in between 0 and 255, accordingly you map the values between black and white. So you divide the total black and white range between some multiple 255 different values and plot them as you can see here. Suppose, can you see this pixel 162? It is not black, it is not white. It is some grayscale 162. Can you see this other pixel 208? Do you notice that 162 pixel has a gray intensity which is different than 208 pixel? Okay, so this is not noticeable very easily, but if you clearly look into the pixel, then you will be able to identify. You can identify here also. There is a pixel value 87 and pixel value 141. You notice there is a difference between the gray values of these two colors. Okay, and it is because they have different pixel intensity. So this is how image is actually displayed on the screen, and this is how image is stored in the storage unit of a computer. So what this 0 to 55, all these numbers mean that I have already explained. In grayscale images, we are talking about what happens in a grayscale images. But in a color images, there will be some other logics also used. There will be three different matrices, one for the red color, other for the green color, and the other for the blue color. For example, if I use a matrix and in that only we have one pixel, suppose matrix containing one row and one column, that means only one element. So this matrix contains number 255, this matrix contains number 255, and this matrix contains number 0. What does that indicate? The intensity of red color is very high, that is 255, that is largest. Intensity of green color is very high, that is largest. And intensity of blue color is 0, that means nothing. So if I mix red color and green color with the highest possible values, and if I don't use any blue portion of that, what will be the corresponding color? So you can imagine, if I mix red color with green color, what will be the resulting color? That color will be produced on the screen when you use color image. So for color image, what I mean to say is, for a color image which is having one pixel, actually there will be three matrices stored in the computer, and those three matrices will be corresponding to three different color intensities, R, G, and T. This is one of the standard color scheme, that is RGB. There are few other color schemes also, which we will learn in detail when we will start with the syllabus. So if I have to visualize a image, wait a minute, yes. If I want to visualize an image with 10 pixels in a row and 10 pixels in a column, that is 10 by 10 image, then there will be corresponding 10 by 10 red, green, and blue matrices. There will be three different matrices for RGB stored in the computer. So that's why color images consume more storage, because as per requirement we have thrice as many number of matrices available in the storage as compared to the grayscale image. So this is about image, what image is. So one simple black and white image is shown here. You can see here 0 represents black color, 1 represents white color. So this is the checkerboard pattern which is shown by using black and white, and this is some other image which is shown by using grayscale. So you can see, if I use a black and white image, it will have only two intensities, and grayscale image can have up to 255 number of intensities or 256 number of intensities. And this is a example image which is shown with the help of uh, pixels. Okay, so as you can see, this image looks dull because here we have used, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This is 20, 21, 22, 23, 24, 25. So you can see we have used horizontally 25 number of pixels to represent that image, and vertically we have used some number of pixels. So I'm not counting, but you can say there are X number of pixels we have used. So if I use larger number of pixels, listen carefully what I am saying. If I use larger number of pixels to represent this same image, then what will happen? For example, instead of using 1 pixel here, if I use 2 pixels horizontally as well as vertically. So instead of 1 pixel, now I have 4 pixels. So the new pixel is of size 1 by 4 as compared to the earlier pixel. So 4 times smaller pixel size I am using, because I am dividing single pixel into 4 multiple pixels. And this same logic I will have to apply throughout the image, horizontally as well as vertically. And in this way we can have smaller pixels. Each individual smaller pixel can be represented by individual color value. So for example, in at this border, suppose I use single pixel like this, then either this pixel can be white or it can be gray. Okay, either this can be white with the collar of that army person, or it can be gray with the outer jacket color. But if I use 4 pixels here, you can imagine, if I use 4 pixels here, then what will happen? This will be total white, this will be gray, and this will be depending on which color has large amount of portion occupied. So gray color has occupied more portion, so this will be probably gray, and this white color has occupied more portion, so this will be probably white. So if I use a single pixel, it can be either white or gray. But if I use 4 pixels in that same area, then we can have different pixels of different color intensities, either white or gray. And in this way, the picture will look more correct. As you can see here, the border of color is not so accurate. As you can see, this border is not so accurate. But if I use smaller and smaller pixels, that border will become more and more accurate. And that's why we can use smaller and smaller pixels, which is called as a more resolution in a picture. If I use smaller and smaller pixels, I can say that the resolution of an image is more. Okay, the definition of resolution and its different types of resolutions we will see later in detail, but this is just an overview. One more thing that I want to tell you is, when image is represented like this first pixel is called as pixel at origin, like how we represented vertical and horizontal axis while sketching an signal. And suppose this is a sinusoid signal, and here this this point is called as an origin, where the time t is equal to 0. In the image we don't have any time t is equal to 0. Instead we have coordinate called as an origin. So this is origin. In this direction we have y coordinate. See, this is very different than the Cartesian coordinate system. And in this direction we have x coordinate. Please remember this, because in general in a Cartesian coordinate system, horizontal axis is the x axis, vertical axis is the y axis. But in the image, vertical axis, the downward, represents the x coordinate, and horizontally towards right is represented as a y coordinate. This origin pixel is said to be located at coordinates 0, 0. Okay, so we say that first pixel is at 0 0. This pixel value 2 is at x equal to 0, y is equal to 1. The next pixel at intensity 15 is at x equal to 0, y is equal to 2. So I hope you understand. In horizontal direction, in the horizontal direction, so x value remains constant and y value increases. This will be 0 1. I will write here. This is 0 0. This is 0 comma 1. This is 0 comma 2. I'm writing coordinates. Coordinate of this pixel is 1 comma 0. Coordinate of this pixel is 1 comma 1. This is 1 comma 2. Then this is 2 comma 0, 2 comma 1 and 2 comma 2. Okay, so this way x increases in the vertically downward direction and y increases in the rightward direction. Please remember this. So with this basic knowledge, we will now see what is there inside a syllabus. So as I said, we have theory as well as lab for this subject. The distribution of mark theory marks is same as earlier. You will have 20 marks for the internal assessment, 80 marks for the end semester examination, total 100 marks. For theory per week, you will have one lab session of 2 hours in a week, and there will be a oral oblique practical examination as that of the earlier semester, same as that of the earlier semester. So in theory, you have total 6 modules, out of which the first is digital image processing fundamentals. You will have to understand what is fundamental steps in image processing, how the image elements are processed by a system, what is image formation model, how actually image is formed from the uh, actual scene, how a digital image is formed, and what are the different types of image file formats, such as JPG, PNG that we have heard so many times. What are those? We will also have to see what is tonal and spatial resolutions that I was talking about in the previous slide. The resolution is more. That means the picture will look or image will look more better. And the relationships between neighboring pixels. Neighboring pixels means, as I showed you, the pixel value at the top left corner is called as located at origin, that is 0 0. The pixel which is on the right side of that is called as immediate neighbor of that pixel. So the pixel, some pixel which is situated at some value will have some. So as you can see here, this is center pixel. There is a one pixel located here. There is one pixel located here, 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 and here. So these all pixels which are around this center pixel are called as neighboring pixels. Okay, so the neighbors which are exactly vertically downward, upward, horizontally rightward, and leftward are called as adjacent neighbors because they are at the closest distance. And neighbors which are at the corners, left top, left bottom, right bottom, these are called as corners or only neighbors. Okay, so these are 1 1 1 1, these are adjacent neighbors, and rest of the 0 0 0 0 are only neighbors, simple corner neighbors. So we will see what are the relationship between these pixels. Then in the second module, we will see image enhancement in a spatial domain. So as I said earlier, in a image, we don't have any time domain. Instead, we have space coordinate, horizontal axis y, vertical axis y. So in a space, we talk about distribution of those pixels. Some pixels are near origin, some pixels are away from the origin, some pixels at coordinate 0 1, some at 0 2, and so on. So we talk about the coordinates, we talk about the space, right? So in a space, how these pixels are distributed, this is what we talk about. We don't talk about any time domain here. So that's why in a digital image processing, we have space coordinate and frequency. We don't have time and frequency now. Please remember, in earlier discussions of all other digital signals, we were having time domain and frequency domain. But in the image, we don't have time domain data because this this these pixel values have nothing to do with the time. These pixels value vary depending on where that pixel is located at. Suppose that pixel is located on the tie of this person, then its value will be different. If it is located uh, on the collar of this person, its value will be different. So it's all about the space. It's all about the location, and that's why domain operations, and we will have frequency domain operations. We don't have time domain here. So we will see in the second module spatial operations and how we can enhance, how we can make that image look more better by using those spatial operations. So under that we have enhancement of the intensity of pixels, enhancement of the distribution of different pixel intensities, and I hope you have heard uh, terms such as contrast enhancement. The contrast of an image means how black and white color differ from each other. So all those things we will be learning in the second module. We'll be also learning image subtraction and image averaging operations. We'll be also learning some special domain filters, which we have basically seen in the workshop that we had earlier. Uh, Low pass filter, high pass filter, where the image will look more blur or image will look more sharp. In the third module, we'll be talking about the image segmentation and representation. So here we will be discussing more about how we can separate out the different parts from the image. For example, if the analysis of a crop, if an analysis of a crop is to be done, and the satellite image of a particular area in a Punjab has been taken, and with the image processing, people want to analyze whether the crop has become fertile or not by looking at the image. So what basically they do, if the crop has become fertile, there will be ends on the top part will be more and more brownish. And if the crop is not fertile, then the ends will not be more brownish. So basically, they will use some image processing technique to identify whether the crop has become fertile or not. So what is the basic or what is the beginning step before we apply the analysis? So before we apply the analysis, it's our task to separate out the crop area from the other soil which is being taken in that picture. Or suppose there is a crop on the left or right side of a highway, then we need to ignore the highway part, because if we apply that image processing on a highway, I will always get a result that crop has not become fertile. Why? Because I'm not examining crop, I'm examining a highway. So its first aim is to separate highway from that crop, and I apply algorithm only on a crop. And to do that, we need to segment the part of interest from the part of non-interest, and that's what is called as an image segmentation. And the representation means after we segment out the unnecessary part and segment the necessary part for the further processing, we need to represent that by using some outer borders or edges on the boundary, and that is called as image segmentation and representation. We will see how to do that. So for that, you can see here the polygonal representation is used. Polygonal representation means, suppose I want to analyze a skull of a human being, then when I take a picture, there will be multiple things on the background of a person who is standing in front of that camera, maybe a X-ray camera or maybe any other kind of camera, MRI image also you can think of. So after taking an image, I will have to analyze a skull. So I will have to highlight the boundary over which there is a skull, and external boundary is to be ignored because there is other background things which are not necessary for my analysis. So to make a boundary around my skull, I should have some kind of shape or some kind of geometry that can fit exactly on outer boundary of my skull, and that can be provided by different shapes or uh, different kind of borders that will be discussed in a polygon representation. So polygonal representation will take different polygons, and it will keep joining them, and finally the result will be as if it is a continuous boundary on around my skull. So this way we can learn image segmentation and representation. In a fourth module, we will see binary image processing. In binary image processing means the image which is having only 1 and 0. The image which I showed you in the PPT here, this black and white image, which has only black color, that is 0, only white color, that is 1. This kind of image is called as a binary image because it has only two different colors. That's why binary. So how to perform different operations on this binary image, that we will be learning in the fourth module. So different operations will be dilation, erosion, opening and closing, hit or miss transform, and boundary extraction, region filling, thinning and thickening, and so on. So we will see what are the applications of these all binary image processing operations. And once we will start learning these operations, you will get to know that these are very there are very beautiful operations of all these very beautiful applications of all these operations. In the fifth module, we will be learning image transforms and frequency domain processing. So as I said, there is a spatial domain, and in a spatial domain, there are only restricted number of operations that we can perform, and only restricted number of uh, productivity that it can provide. So instead, if we convert that image to the frequency domain from the spatial domain, we will get more advantages, as we saw in the time domain and frequency domain also, that the frequency domain will be easy to deal with. The convolution is easy in a frequency domain, and so many things we have seen in the earlier syllabus. The same advantages we will have here for the frequency domain processing, and hence we will see all the frequency domain processing. So here we will have as I showed you, the image will have pixels in the horizontal direction and the vertical direction. So as we saw in the image, we have samples in the horizontal axis, samples positioned on the horizontal time axis. But in the image, we have samples everywhere on a horizontal as well as vertical direction on the space coordinate, and that's why we have to basically deal with a two-dimensional Fourier transform. So we have to basically discuss about what is two-dimensional processing of a Fourier transform, and then the fast Fourier transform and how it is applied on the image. So we will learn that. Then we will see some other transforms such as discrete Hadamard transform, DHT, fast Hadamard transform, cosine transform, and discrete wavelet transform. So these will be the specific transforms which are very popular in the digital image processing in a frequency domain, and we will be learning them. And as we saw here in the second module, how we can low pass filter and high pass filter the image in a spatial domain. The same we will learn here in the fifth module, but here we will be learning that same low pass and high pass filtering with the help of frequency domain now. Okay, so the things are much simpler as compared to the earlier syllabuses, but the only thing is you need to be logical. You need to listen, because if you don't listen, then logical reasoning is not that easy. For example, if I explain what is a XOR logic, And if someone doesn't listen to the explanation of XOR logic, and he simply want to give some input and want to see what output he is getting, he will have to waste a lot of time in understanding what exactly happening when the output is becoming 1 and when the output is becoming 0. Instead, if he listens and if I give him only a truth table, he can easily analyze and can tell me that when both the inputs are same, output is this. When both the inputs are different, the output is this. This way, you need to be a good listener and think logically to understand the subject. There is no more difficulties in this subject. The last module, that is sixth module, is the image compression module, where we'll be learning basically how we can store the image with less amount of storage. Okay, how we can reduce the storage requirement of an image. So basically, we will be learning uh, some applications of different coding techniques which we have already learned, such as we have also learned Shannon-Fano coding, we have learned Huffman coding, we have learned what is coding redundancy, coding efficiency. So I think you might have learned this all in the digital communication subject. Please reply. Have you learned what is coding redundancy, Huffman coding, Shannon-Fano coding? Have you learned that? Please type in the chat box. Okay. So the applications of these all will be learning here again, and that's why it's not so difficult. And at the end, we will see lossy compression technique. So there are two types of compression techniques because we compress image. That means we will be reducing the storage requirement. So when we want to store the data, but at the same time, if we want to maintain the quality, it will become difficult. So there are some techniques which maintain the quality but provides a poor compression. And there are some other techniques which disturbs the quality by certain amount but provides a very good compression. Listen very carefully. If I have some image, I can store that image in two different ways. One way is to keep the quality of image very good, and other way is it is okay if the quality of image is little bit degraded. So in first application, when you want to maintain the quality, the compression will be very poor. The storage reduction will be very poor. And in the second case, when you are okay with the degraded quality, the storage compression will be very better. So you can store that image in a very small space. So the first technique where you don't want to lose anything is called as lossless compression technique. And the second, where you are ready to lose some amount of information out of that image, is called as lossy compression technique. So the first few are the lossless, and in the last sub module, we will be learning lossy compression technique, where the compression will be very greater amount of compression, but the quality of image will be degraded by that same amount. Okay. These are the popular books that are specified in your syllabus. This is the very popular one among reference as well as textbooks. Though it is listed in a textbook category, it is good. It can be thought of as a good reference book also. Rafael C. Gonzalez and Richard E. Woods, Digital Image Processing. This book is available in a library. A very good book. Another book that you can refer to is Anil K. Jain, Fundamentals of Digital Imaging. However, I prefer using Gonzalez and Woods. There are few other books such as Dhananjay K. Thekadath. The books are not listed here, but I will give a list of that also. If someone has that, they can refer to that other book also. Otherwise, this is good. Okay. If you have any doubts, you can ask. This is all about syllabus. We have 6 modules. We have total 48 lectures to be utilized to understand the whole syllabus. Please unmute and ask your doubts if you have any. Okay, people are saying no doubts. So, anyways, we'll start with the syllabus in the next uh, lecture. Okay. Till then, see if you get hard copy. Otherwise, you can use a soft copy of a book also. If possible, I will share the soft copy. I will create a Google Classroom for this, and I will share a code in the WhatsApp group. Please join Google Classroom as early as possible, because people join late and then they keep on asking about the joining code. Okay, so please join as early as possible. Uh, it will be beneficial for me as well as for you. So let's conclude today. Thank you for joining. You can leave me now. Thank you.